welcome back. Today's topic, last one for the unit, so you got a quiz coming up, is quadratic functions, and then we'll look at a couple of applications of quadratic functions. Now, we've done a lot with quadratics, and actually we've seen quadratic functions before, so hopefully some of this will be some good review, and then we'll just kind of build on what we've talked about before. So remember what it means to be a function versus the equations that we've spent the first part of the unit on. A function is still an equation. The difference between these equations and the ones we looked at before is when it's just an equation with one variable, we solve for the one variable. If your equation has two variables, then that relationship between two variables we can graph, and if it follows certain rules, then we call it a function. So a function is an equation, but it's relating two variables, usually x and y. And remember, every x value can correspond with exactly one y value for it to be a function. And if it is quadratic, right, if it's a quadratic function, that means that it has a degree of 2. It's got an x squared in it, okay? And we know, hopefully, we remember what the quadratic function looks like. Remember the parent? What is our parent quadratic function? It is the y equals x squared with nothing else being added or subtracted or multiplied. There's our basic. So all quadratic functions are just some transformation of that parent. So just to dust off the cobwebs, let's graph our parent function, make sure we remember what it looks like. So when we graph this, we're just going to pick a couple negative, 0, a couple positive, make sure we can make our picture. What happens when we plug in a -2? Well, -2 squared makes a positive 4. Plug in -1 squared makes a positive 1. 0 squared makes 0. Positive 1 squared, positive 1. And positive 2 squared makes positive 4. Okay, so we're going to graph this function here, and I apologize for this graph. I meant for these to be the axes, and this to be the origin here, and then 1 and 2 and -1 and -2. Okay, so I'm sorry that didn't show up so well, but we have a point on our graph. We said -2 squared was going to make 4. -1 squared made 1, 0 squared made 0, 1 squared was 1, and 2 squared was 4. And here we see the shape we hopefully knew was coming. This is what all quadratic functions... Wow, I missed. Try to actually, connect the dots when you graph this on your own, but this is what all quadratic functions are going to resemble. All quadratic functions make this U-shaped graph that we call a parabola. And to be specific here, we say that this parabola opens up, and that is from the origin, right? It's opening up. The branches go up instead of going down. If it was flipped over, then we'd say it's a parabola that opens down. Now, there are some features of a parabola that you should be able to identify. So let's look at this example here and try to identify some of those features. So y equals a negative x minus 3 squared plus 1. Well, I'm hoping we remember that this negative reflects the graph over the x-axis, that this minus 3 makes the graph go to the right 3, and that this plus 1 makes the graph shift up 1. Right? I'm hoping we remember those transformations, but ultimately we do have a graphing feature here. So if we were to graph using Desmos, y equals a negative x minus 3 squared and then plus 1, we see all those transformations that we just identified there. So if I'm going to make this graph, we've got a point at 3, 1. We've got a point here at 2, 0. We've got a point here at 4, 0. And this is probably going to get confusing, so let me get rid of this. And then, let's see, we got another good point here at 0, -8. And, alright, so that's probably good for now. Let me put my calculator away. Let's see. Sketch this out. Really the same thing's going to happen over here, right? This graph has symmetry. So we have, if we go down one left or down one right, we see those mirror image points. The same thing is going to happen here. So I'm going to reflect this point, make it, oops, make its mirror image just so it's a little easier for me to connect the dots here. So we have a parabola that opens down. Okay, again, that should make sense because of that negative. All right, so the characteristics of any parabola that I want you to be able to, excuse me, to identify, the most important is what we call the vertex. And I think we've talked about that before, but if you were to describe to someone this point right here, that is the vertex. Goodness, this point right here, that is our vertex. So we have a vertex at 3, 1. That's going to get mixed up in all my stuff. That's the vertex. How would you describe to somebody what the vertex is? Like here it's the top of the graph, but in our other parabola it's the bottom of the graph. So top or bottom, maybe. I think the best way to describe this is the turning point. It is the turning point. What does that mean? So if you read your graph from left to right, what's happening is we're increasing until we get here, then we turn, and then we're decreasing, or vice versa on the other parabola. Okay, so it turns, it changes direction. Hit the undo too many times. Okay, so the turning point. And yes, it will either be the top or bottom point. The high or low? I'm not sure. The top or bottom? High or, oh. Let's keep these consistent. High or low point on the graph. Maybe I wanted highest or lowest. That would make more sense. I don't know that I made those blanks long enough to fit those words in there. It's either going to be the highest or lowest point on the graph, the top or the bottom of the graph, depending on whether your parabola opens up or opens down. So if it opens up, it's the highest, or actually if it opens up, then your vertex will be the lowest. If it opens down, it's the highest. Okay, so you should be able to identify the vertex for any parabola, and that was pretty simple using Desmos. I just tapped on the point and told me where that vertex was. You should also be able to identify the x-intercepts. So x-intercepts are the points where your graph touches the x-axis. And x-intercepts have a couple of names. We could also call them roots. I don't know if you've heard that before. You could also call them zeros. Okay, so zeros or roots or x-intercepts are all the same thing. They're all referring to points where your any graph, when in this case a parabola, touches the x-axis. So we have two roots right here. I like the word root versus x-intercept. It's just easier to say it. So we have a root here, and then we have another root here. Those are the 2 points where your parabola touches the x-axis. So it's possible for your parabola to have 2 x-intercepts, but that's not the only possibility. If your parabola had a vertex on the x-axis, if the vertex was on the x-axis, then it would only have 1. And then if your parabola was somewhere maybe like this, then there's no way it would ever touch the x-axis because it opens up forever from a point above it, or maybe down here, then it's possible for it not to touch the x-axis at all. So typically, you're looking at 2 x-intercepts, 2 roots, but it's also possible for there to be 1, and also possible for there to be none. All right, so x-intercepts, or roots, or zeros, where your graph touches the x-axis. And then we have y-intercepts. This is going to be where your graph touches the y-axis. Now, how many y-intercepts are you going to have? Exactly 1 every single time. No matter where your parabola is, eventually it's going to cross through the y-axis 1 time. Okay, so on this particular graph, our y-intercept is right here. And again, that point was identified from Desmos. Okay, the last thing is something I mentioned a second ago, that this parabola has symmetry. So we have symmetry. What color do I want to use here? Let's go with this awful blue. Symmetry, and if we just cut this graph in half through this really bright blue color, that line that cuts that parabola in half, we would call the axis of symmetry, because it is a line, symmetry, that cuts that parabola in half. So the axis of symmetry is a vertical line. Now if it's going to cut the parabola in half, it has to go through the vertex, and then it cuts the parabola in half. Now if I was to ask you where that axis of symmetry was, technically there is an equation for that vertical line. In this case, a vertical line is always an x equals equation. In this case, it goes through an x value of 3 at every single one of those points. So we would say this axis of symmetry is at x equals 3. Okay, so always an x equals number, x equals equation. Okay, so those are characteristics of any parabola that you should be able to identify. Now, some of them you can see just by looking at the equation depending on what form it's in. So you're going to see quadratic functions appear in a couple different forms, and I want to make sure you can identify or maximize what you can identify from each of those forms. So we're going to start with this, which we should hopefully know something about. Just by looking at this function, what do we know? Again, this negative here says that this graph is going to reflect over the x-axis. And this -2 makes the graph go to the right 2, and this +9 makes the graph go up 9. Now, when I'm saying this graph, I mean the parent function. If the parent function were to shift right 2 and up 9, that means the vertex shifts to the right 2 and up 9. So just by looking at this function, I know it's going to be opening down. So this, we can say that. The reflection over the x-axis, oh, I guess I can do that. This also tells me that the parabola opens down. Okay, and the right 2 and up 9 tells me that the vertex is going to be at right 2 up 9 at 2 and 9. So instead of having a vertex at 0, 0, we shifted right 2 and up 9, and then we have a parabola that opens down from that point. So just by looking at this, now we call this form vertex form. This is what we call the vertex form of a parabola. Vertex form, the general vertex form, which I think we've put in notes before. General vertex form, if we took out the numbers, we would be looking at y equals a x minus h squared plus k. Why do we call this vertex form? Well, as you saw here, we can identify transformations and know exactly where our vertex is going to go. So the vertex form shows us which way the parabola opens, and it's going to show us where the vertex goes because of the transformations. So we call this vertex form because it reveals about the graph. It reveals the vertex and the direction of openness, whether we open up or open down. And that's a real word, openness. Okay. Excuse me. All right, now, let's say we take this exact same function and we were to simplify it out. So if I said take this function and simplify it out, that means take the x minus 2 and actually square it out, and then go ahead and add the 9 and multiply, simplify it out. If we were to do this, let's see, we're going to get an x squared, and a negative 2x and negative 2x would give me a negative 4x. And then a negative 2 times negative 2 would be a positive 4. If I distributed it in the negative, it makes it a negative x squared, makes it a positive 4x, and it makes this a negative 4, and now I can actually add the 9. So we'd be looking at a negative x squared plus 4x, and then negative 4 and positive 9 makes a positive 5. Now this should look familiar based on the solving that we did, where we have ax squared bx plus c. This is what we call standard form. All right, standard form, where we have ax squared plus bx plus c. Now notice the a that's here and the a that's here. That's the same a in both of them. Now what did a tell us in this one? We had a as a negative 1, told us the graph was going to open down or reflect over the x-axis. That's still going to be true. So just by looking at this, this is telling me that this graph opens down. But what else does it tell me about this graph? Well, let's actually look at the graph. Okay, I think you're going to see it. if we put in y equals a negative x squared plus 4x plus 5. Let's see if there's a connection between any numbers we see on the graph and any numbers that we see in our function. So the vertex is at a 2 and a 9. We knew that from the other form, but from this form I don't see a 2 or a 9 anywhere. Let's see, it crosses the y-axis at 5, and that is going to be what this graph tells us. When we have a y-intercept, in this case y-intercept is 0, 5, when we have a y-intercept, that means the x value is 0, okay? Think about this function. If I was to plug in a 0 for x, if the x value is 0, 0 went there and a 0 went there, what would be left? The only thing that would be left would be this positive 5. So no matter what, in your standard form, if you put a 0 in for x, that leftover constant is going to be where your graph crosses the x-axis every time. So this number here is always going to be your y-intercept, okay? So standard form, I don't know if it's as helpful as the vertex form. I think vertex is the most important part of the parabola, so I prefer vertex form. But standard form, just by looking at this standard form, I know that my parabola is going to open down, and I know where it's going to cross the y-axis. So this one tells me the direction of openness, and it also tells me the y-intercept, which is going to be at C. Actually, technically 0, C. So whatever C is right here, that's going to be where your graph crosses the y-axis. And here I should have said also, to be more specific, your vertex is at H and K. So it's the opposite of this number, and we keep that number the same. Okay? Now, let's take this form here, this simplified form, negative x squared plus 4x plus 5, and let's factor it out. If we were to factor this, we would take the negative out first. X squared minus 4x minus 5 would be left. And then factors of negative 5 that make negative 4 would be negative 5 and 1. So we would have a negative, and then an x minus 5, and an x plus 1. So what does this form tell me? Well, if we go back to this graph, look where it crosses the x-axis, at negative 1 and at positive 5. Negative 1, which is a solution here, and positive 5, which is a solution here. Or these are the values that that's zero out those factors. That's why sometimes your x-intercepts are called zeros. So x equals 5 would be a solution here. It would zero out the y. And then negative 1 would be a solution here if this were an equation. So this shows me, let me change the colors on this. If we took this and factored it, x equals 5 and x equals negative 1 are my roots, my x-intercepts. So we have roots, x-intercepts, zeros, whatever you want to call them, at 5, 0, and negative 1, 0. So this is the same three functions, or the same function in three different forms, and all the forms are helpful for their own reasons, okay? This one we call, go back to pink here, factored form. And factored form is where you have y equals, and then you're going to have x minus a root and x minus another root. And this one is helpful because, again, based on this number here, you can still see which direction it opens, so all the forms are going to tell you that. And direction of openness. Oh my. Don't mind my spelling. And more importantly, it tells us the roots. I should be able to tell by looking at my factored form that 5 is a solution and negative 1 is a solution, so this thing would cross the x-axis at 5 and at negative 1. Okay, so I want to be able to quickly identify the roots at R1 and R2. R1 and R2. Okay. Okay, so they all show you direction of openness, but the important piece for vertex form is that it shows you the vertex, and then for standard form it shows you the y-intercept, and then for factored form it shows you the roots. Okay, so not that you might in a real situation be asked to do this, but I gave you here 3 equivalent forms. This is the same quadratic function, but one's in standard form, one's in vertex form, one's in factored form. And because you have the equation in all 3 forms, you should be able to graph this without having to use any technology, although your technology should be able to verify for you. So if you want to pause and give this a shot, we're looking here at the factored form. This is the factored form. Just by looking at this, well, here I know that my parabola is opening down, and then the 1/4 I know is going to be a vertical compression of my parabola. But more importantly, I can see here that x equals -6 and x equals +2 are going to be my roots. So I'm going to have a root, or an x-intercept, at -6, 0, and +2, 0, because -6 would cancel out the +6 and +2 would cancel out the -2. Okay, so I can graph that. This is going to cross the x-axis at -6 and at +2. Okay, now this one is our standard form. This is all multiplied out. Our standard form again shows me that it's going to open down, and that 1/4 is going to be a compression of the graph, but more importantly, this tells me where this graph is going to cross the y-axis. So this is going to, based on this function, have a y-intercept at 0, 3. So here, looking at that, here, looking here, and here. Okay, so I'm going to graph this y-intercept at 3. Means we're crossing the y-axis at 3. And there's symmetry here, so if I, from this root, can go over to and up 3, I can do the same thing from the other root in the opposite direction. So I'm going to go over to up 3 and make that mirror image point. Okay, and then the last one is our vertex form. Again, I can see opening down and the compression, but now I can also see from this number and this number that my vertex is going to be at -2 and +4, because I have a shift to the left 2 and up 4. So at -2, +4, and that makes sense based on where the other points were. So now I can connect these and make my parabola. So here it is. Okay, and if you wanted to confirm your work, you can put any one of the forms in the calculator. So -1/4. And then I'm going to just use the first form, x + 6, x - 2, just to confirm. And there it is. -2, 4 was the vertex, 0, 3 was the y-intercept, 2, 0, and -6, 0 were my roots. Okay, so everything confirmed. Alright, so you should be able to identify the different forms and realize why the different forms are helpful. Okay? Now, I want to show you a couple of applications of quadratic functions, a couple places where they're useful. Now, this first example is not really practical, but it's a situation we could model using a quadratic function. So we have Johnny hitting baseballs off a tee, and the following equation gives the height of the baseball after t seconds of his last hit. So his last hit can be modeled by this function. First thing it says to do is graph it, and I'm going to use Desmos for that. So -16, we're going to use x in place of t squared plus 32x plus 3. And here's our function. Okay, so this is starting on the y-axis at 0, 3. Does that make sense? Well, it says he's hitting baseballs off a tee 3 feet high, so that makes sense to me. So right here at 0, 3 is our y-intercept. And then the vertex is at 1 and 19. So at 1 and 19 we have our vertex. And then it's got a x-intercept at 2.09, so somewhere here-ish, 2.09, comma 0. Now the other x-intercept would be a negative. Nothing negative is going to apply in this real situation. That's why this graph is all confined to quadrant 1. So if you want to just tap on the graph, you can find additional points, you know, like, let's see, what's happening at 1, if I can get there. At 1, oh, we're at 1 and 19. How about a half? Silly. At a half, we're at 15. So at 0.5, we're up to 15, just to make this a little bit more accurate. And then that can be reflected. So I think this is good for us here. So we're graphing, wow, maybe your graph looks a little smoother than mine, but let me put this away for a second. Should make sense, this picture modeling this function. So Johnny hits a baseball off a tee. The baseball starts 3 feet high, goes up, reaches a maximum height, and then comes back down and hits the ground. Okay, so what's the maximum height the ball reaches? The maximum height the ball reaches. Now notice here that this is height and that this is time. Okay, so maximum height the ball reaches, we can see it. This is the maximum height the ball reaches, and that maximum height, that maximum y value is 19. So the maximum height the ball reaches is 19, what's the units here? Nope, no units. Gives the height h of the ball after t seconds. So just, oh, it's here, feet. Just kidding. Okay, so 19 feet. How long does it take for the ball to reach the maximum height? So that was the other part of the vertex. This was a time of 1 second. So this is t and this is h. It took 1 second to reach that maximum height. Let me use a different color here. 1 second. Okay. What is the height of the ball at 1.5 seconds? So 1.5 seconds, I think I plotted that one exactly, but if you weren't sure, at 1.5 seconds, technically that's an x value of 1.5. You could go in here and put in x equals 1.5 and see exactly where that line hits the graph. So then you can see at 1.5 the y value that corresponds is 15. So 1.5, point at 1.5 and 15 tells me that it's going to be 15 feet high. And that is here. Okay, at what moments is the ball at a height of 10 feet? So 10 feet is here. We could kind of, oh, I already used yellow. We could do the same thing we just did a second ago. All right, not used yet, this funky orange. Okay, so 10 feet is here. It's obviously going to hit a height of 10 feet twice, once on the way up and once on the way down. So I need to know the coordinates here and the coordinates here, and we can get that from Desmos. So I want to know what's happening when y equals 10. And now it shows that same line that I just put. Let me get rid of this. Same line that I just drew in there at, not 1, 10. At 10, and then I can put tap on those intersections to see. This point is at 0.25 and 10. 0.25 and 10. And then this point, tap on that one, is at 1.75 and 10. So that tells me, go away calculator, that it's going to hit 10 feet at 0.25 seconds and 1.75 seconds. Okay. After how many seconds does the ball hit the ground? Well, it's hitting the ground over here. This is when the ball hits the ground, right? It's at a height of 0. And that height of 0 happens and 2.09 seconds. So in 2.09 seconds, the ball is at a height of 0. And then the last piece here is just the contextual domain and range. So the domain is your x values, or in this case, x's are time. And then the range is normally your y values, or in this case, it's height. Now, if there was no context here, technically your parabola goes left and right forever. So when you're looking at the domain, we would say the domain would be everything from negative infinity to infinity. But the domain is restricted here. So domain, the times, the smallest time to the largest time. The smallest time that's reasonable is 0 seconds. And the largest time that's reasonable is 2.09 seconds, because after that the ball's on the ground, nothing's happening. So from 0 to 2.09, and we can include those endpoints. And then the range is the y values, it's the lowest to the highest, or the heights. What heights make sense for this situation? Well, the lowest height is when the ball hit the ground at 0, and the highest height was when the ball was at its peak there at the vertex at 19. Nothing after that, nothing before that makes sense for this particular problem. So this range is everything from 0 to 19. So this is domain, and this is range. Okay? So you should be able to graph a function, and if it represents a scenario, understand what's going on in that scenario. Okay? And then there's this. I think these are a little more useful in terms of applications. So the value V in thousands of dollars of a certain stock after M months is given, or for a certain company is given by V of M equals M squared minus 6M plus 13. What is the lowest value the stock will reach, and when will it reach that lowest value? Now, if I gave you a quadratic function, even without asking you any questions, what would you try to do with your quadratic function? Well, hopefully if I gave you an equation, you'd be trying to solve it. If I gave you a function, graph it. Okay, that's what we do with functions, we graph them. So let's graph this quadratic function, x squared minus 6x plus 13. Okay, so here's our function. And this represents value after m months. So the x-axis is the m-axis, and the y-axis is the v-axis. So in place of x, we have m. In place of y, we have v. Okay? So we have a lowest point happening right there. So we have that is the lowest point. That's where everything that's important to this problem is happening. So we graphed this function, and it showed us a vertex at 3 and 4. Okay, and that's going to be how we answer this question. Anytime you're dealing with a quadratic function and you're asked to find a highest or a lowest or a max or a min, you have to be looking at the vertex for that parabola. So we just have to interpret this, because we're asked 2 questions. We've got 2 pieces of the vertex. What number answers what question? So what is the lowest value the stock is going to reach, and when does it reach the lowest value? So on our graph, this normally represents an x value and a y value. But what do we have in place of our x's? We have m's. And what do we have in place of y? We have v. That means the 3 represents an m. The 3 represents a number of months. And then a 4 represents a v, or a value. So this says there's a lowest value of what is it, $1,000? $4,000 in exactly 3 months. Okay, that's that. So if you want to try out the next one, give it a shot. Feel free to pause. But otherwise, we're looking at the profit in dollars for a company which produces G amount of goods, and it's given by this function. This time we're looking for a max. Now notice it's a max here. This was a min because the parabola opened up. Here we have a parabola opened, opened up. Here our parabola is going to open down, so we're going to be looking for a max. Max profit and the number of goods produced then. So we're going to need to find the vertex. And here in place of x we have g, in place of y we have p. So let's graph this bad boy. Negative x squared plus 980x minus 3,000. And this might take some zooming. We've got some large numbers happening here. Lots of zooming. Okay, I'm trying to stretch that axis out. There we go. Okay, so a little bit of zooming, and that vertex, that's what I need. So this one has a vertex at 490 and 237,100. That's the import piece. That is the max of this parabola. Now we just have to interpret. So again, normally this represents an x and a y, but in our function, in place of x we have g, and in place of y we have p of g, or just p. So that means the 490 represents a g value, or a number of goods, and the 237,100 represents a p value, or a profit value. So this tells me that there is a max profit of $237,100 for producing 490 goods, whatever it is they're producing. Okay, so if you have a quadratic function, you're asked to maximize or minimize or find the highest or the lowest or largest or smallest, you are looking for the vertex and trying to identify what it means in that problem. Now, number 3 is going to be the same concept, but it's going to take a little more work to figure it out, and I'll show you. So Gabby's fencing a rectangular garden using the side of her house as one side of the rectangle. What is the maximum area? That's my clue that I'm looking for, the vertex, that she can enclose with 40 feet of fencing, and we're trying to find what dimensions are going to yield that maximum area. So you can see it's a little different. We don't have a quadratic function to start with. So let's just try to lay out our information here, right? Well, that's no good. She's got her house, and butting up to the house, she's going to fence in this rectangular garden. Okay? So this is the house here, and then this is the garden that she's trying to fence in. Okay? Now, we're trying to find the maximum area she can enclose with 40 feet of fencing. If she puts 40 feet of fencing around this thing, that's the perimeter of the garden. So this 40 feet of fencing represents perimeter. Now, I don't know what these dimensions are, so I'm just going to call this side x, and then this side would have to be the same. This side I don't know is going to be the same, could be different, so I'm going to call it a different variable. I'm going to call it y. If I add those 3 sides together, that's my perimeter, right? So my perimeter is x plus y, or 2x plus y. Now in this case, my perimeter is going to be made up of that 40 feet of fencing. So I'm going to say 40 equals 2x plus y, okay? Now let's hang on to that for a second. I can't find a vertex of a linear function, and that's what that is. So I got to go back to what I'm trying to maximize. What I'm trying to maximize is the area. So I need a function for area. So area is x times y for this rectangle, right? Or any rectangle, length times width. Now that's not a quadratic, so I still can't find a vertex yet. But there's also this issue of 3 variables, and I only need 2 for a function. So that's where the perimeter is going to come in here. If I took this perimeter function here, and let's say I solved it for y would have to equal 40 minus 2x, right? If I just subtract the 2x over, well, that's helpful because if I know what y is equal to, then I can replace y with that expression. So I can make this area equals x times, instead of y, I put in what it's equal to, which is 40 minus 2x. Now if I multiply that out, I get 40x, and then minus 2x squared, and there's a quadratic. Now I can find the maximum, find the vertex of that quadratic. So I'm going to put that in. I'm going to put in my 40x minus 2x squared, and go back to a semi-normal zoom here. Okay, and there's my vertex at 10 and 200. So I got a vertex at 10 and 200. Now it says what dimensions yield, or what's the maximum area and what dimensions yield it. Now let me go back here. This is normally an x value and a y value. Well, I still have x values here, so this still represents an x. But this oops, I'm sorry. So I still have an x here, but y isn't a y, right? Y is an a. So x is an x. It represents this dimension of my garden, and a is area. So I'm going to have a max area of 200 feet squared with dimensions of 10 feet. That was one dimension. And what does the other one have to be? So let me go back over here. If this was 10 feet and this was 10 feet, that's 20 feet, right? I had 40 feet of fencing. So this has to be 20 feet here to make 40 all together. Does that make sense? Let me put this in another color so you can see it later. Right? If that was 10 and 10, this would have to be 20 so that I have 40 all together. I'm trying to get 40 all together. So, and 20 feet is that last dimension. Okay, that's probably about as tough as it can be. But remember, if it's max or min or highest or lowest, you're looking for the vertex. All right, so hopefully we're good. If you have any questions or run into any issues, again,